Hello everyone. So today I'm going to talk about Vitali covering theorem for my presentation for the measure theory course. But before we go to the definitions and lemmas we're going to prove in the proof of the theorem, I'd like to paint a picture of what the theorem states roughly. So it basically says that given a large collection of sets that cover some set E, the Vitali theorem selects a disjoint subcollection that covers almost all of E. What does it mean? So when we say sufficiently large, we are a bit ambiguous. We don't know what we mean really, but we're going to properly define what this means later on. But for now, basically it says that given a large collection, we can derive a small sub-collection from this large collection, such that the sub-collection consists of disjoint sets, where the difference between E and the union of these disjoint sets will have measure 0. So we're at this point familiar with what almost all E means in measure theory. Just like everywhere else, it means the measure of the set difference between E and the subcollection is zero. So one way to use this theorem is like this. So in general, when we're given a set and a covering set which has simpler elements, for instance, when we're given a set E and a covering set which constitutes of certain intervals, boxes, or rectangles, things that are easy to work with in measure theory. We can have a rough idea about the measure of E looking at the cover. We may have a supremum by adding up the measures of these smaller sets, but it's usually not that ideal. So this theorem allows us to create a subcover of disjoint sets, which will give us almost all of E in terms of measures, which may be pretty useful in other areas of measure theory. So that is one use of the theorem I can think of. All right, so before we start, so there's a very easy definition. Semi-disjointness. So a collection of sets is called semi-disjoint if no member of the collection is contained in any different member. We know what disjoint means, but we are weakening that property by saying we are allowing sets to intersect with each other, but they cannot contain one another. That's what semi-disjoint means. So here are a few small examples, very basic examples. Naturally, if the collection has pairwise disjoint sets, it automatically becomes semi-disjoint because they have empty intersections. If the collection is just involving these two intervals per se, then it's an again semi-disjoint collection because even though they intersect with each other, they do not contain one another. All right, our first lemma. So the importance of this lemma is not because of its statement. We're not going to directly use the statement in the proof of the theorem, but because the way we construct the subcollection in this lemma is almost exactly the same as we do in the proof of the theorem. So it's a nice exercise to see it here as well, because some of the properties of the collection are things we're going to use in the proof of the theorem as well. So let's first understand what the lemma says. Let subscript B be a collection of balls contained in a bounded subset of Rn. Then we may find a finite or countably infinite disjoint subcollection Bi, such that union of B's is contained in the union of Bi primes, where Bi prime is a slightly modified version of Bi. They're concentric with Bi's, but their radiuses are 5 times larger. Furthermore, we can make this Bi prime be semi-disjoint. Well, it's a pretty easy trick. So the main part is to derive such Bi primes and construction of these Bi's, the collection of these Bi's. So basically, if we are in a bounded region in Rn, we may have a collection of a huge number of balls that is still sitting inside our bounded subset, but we can refine it in a finite or countably infinite disjoint subcollection BIs, such that this holds. All right, so this part is actually pretty important for the proof of the lemma as well. The way we construct this subcollection BI is very essential to the proof as well, proof of the theorem as well. So we do it inductively. First, we define B0. It is the supremum of the diameters of B's in our collection, subscript B. So we choose B1 from this collection such that B1's diameter is larger than half of the supremum of the diameters. There's a reason we're doing this. First, we're going to use the geometry of this fact. We're going to play with the numbers. So this 1/2 is important because of that reason. Second, we want to see that as I goes to infinity, these diameters go to 0. All right. Once we pick our first element, B1, we pick the second element by considering the elements of subscript B such that B intersection B1 is empty. So what we're essentially doing is we look at the sets in B that do not intersect B1. We look at the supremum of those. Then pick B2 in this set, this collection. So this collection, subscript B, it's supposed to be subscript B, such that B1 and B2 intersection is empty, and B2's diameter is, again, larger than half of B1. So first, let's see if this makes sense, because this supremum could have been infinity, but we're working in a bounded region. So this entire collection subscript B sits in a bounded set. So this supremum cannot be infinite. That is for one. So this second supremum is also cannot be infinite. So the choices of D0 and D1 make sense. Second, we can, if D1 is 0, though, then the selection terminates, which we will consider in a few minutes, but the choice of D0 and D1 makes sense. And since we're looking at the supremum of these things, there exists a B2 such that diameter of B2 is larger than half of D1, because this supremum guarantees that if it's non-zero. All right, let's say at the mth step, the m is 0, then the process naturally terminates. We would have finitely many elements. But if it doesn't, we would have countably infinitely many BIs. All right. So one of the reasons we choose this subcollection this way is because this construction guarantees that these BIs are disjoint, because we are choosing these BIs that way. So we chose B2 from sets that have empty intersection with B1, and B3, or in this case, Bm plus 1 from sets that are disjoint from union of BIs we have chosen so far. So each BI and Bj, given that I and j are different, have empty intersection. The second property is if B is in subscript B, then either B is in our subcollection or B intersects with some BI with 2 times the diameter of BI is larger than the diameter of B. This is also true, because if it was not the case, since we're exhausting our collection B, subscript B, by choosing these Bs, if this does not hold, then B is a viable candidate for our subcollection, then we would simply add B to our subcollection. So every B is either in our subcollection or intersects some of our BI with 2 times diameter of BI is larger or equal than diameter of B. So here I'd like to observe a few facts. Because we're in a bounded region and these BIs are disjoint, the summation of their diameters is finite. But this implies, from basic calculus, the general term must go to 0. So this. Of course, this is in the case of there are infinitely many balls are selected. I mean, we're in a bounded region with balls of radius diameter bi over 2. So since the region is bounded, their summation must also be finite. Anyway, in either case, either if B is in our collection or B intersects with some BI with 2 times diameter of BI is larger than diameter of B, we still have this property. Because from Euclidean geometry, if this holds and their intersection is non-empty, then it means B must sit in BI prime, because BI prime is the ball with radius 5 times BI. And it guarantees because of this property. But this concludes our lemma, because almost concludes our lemma, because what we wanted to show was this inclusion. And if each B is in some BI prime, then the union of B's is just inside union of BI primes. And to make them semi-disjoint, simply we can remove BI's if BI prime is in J prime for a different J, and we would be done. All right, so that concludes our first lemma. Our second lemma is a bit more technical, and we dive straight into Hausdorff measures properties. So let E be a Hausdorff measurable set with finite measure, and let E epsilon be given, and there is some rho depending only on E and epsilon, such that for any collection of Borel sets, UI with UIs have non-zero diameter, and they are smaller than rho, we have this inequality. We're going to use this strictly for the second part of our main theorem. Let's dive to the proof of lemma 2. Because of the definition of Hausdorff measure, which is an infimum over deltas and row covers, let's say, this always holds, because this is the infimum over such sums already. And this could be equal, because if E was just these sets, then we would have equality, but we are adding an epsilon, so this inequality always holds. So this is always strictly larger for any row cover Wi of E. And given the Borel sets, as described in the lemma, we can find the row cover Vi that satisfies this equality, just like this, with the same arguments, because this is a Hausdorff measurable set, because these are E is Hausdorff measurable with finite measure, and UIs are Hausdorff measurable, so their difference is Hausdorff measurable, and we can find such an open row cover. Sorry, not open, but row cover Vi for self-habit from topology. All right, now VIs are a row cover of this set, E minus union of UIs, and UIs are a natural cover for, again, row cover for UIs themselves. So when we combine all these sets, the collection of UIs and VIs is an open cover for E, naturally. Then we're going to use this property. Because collection of UIs and VIs are an open cover for E, then we have exactly this. But then we can write the measure of E intersected with union of UIs like this, because this is a Hausdorff measure, and they all have finite measure. Then this is smaller than this. We're just plugging in this inequality here, and this inequality here to here and here respectively. But then adding these up, we have the required inequality. This guy is larger than here, which is the statement of our lemma. All right, now we can come to our main theorem. First, of course, we need to define the word sufficiently large, as we promised in the beginning. Let's start with the definition. A collection of sets, script V, is called a Vitali class for E, the set E, if for each x in E and any delta positive there exists a U with x is in U, diameter of U is non-zero, which is important, and it's smaller than delta. All right, let's give an example of a Vitali cover for two different sets. These are simple sets, but anyway. So if the set is a singleton like 0, and we can just take balls with radiuses 1/2i, then naturally we can find a small enough ball with radius smaller than delta for 0, which is a single element in our E. If the set is an open interval, we can pick balls with rational radiuses. If also we pick any rational x as well. So if we pick any rational x in E with a rational radius, then we would get a countably infinite Vitali class, which is the purpose of this example. So when we say sufficiently large, we don't necessarily mean too large in general. They could still be countably infinite to start with. All right, let's look at our theorem. So let E be a Hausdorff measurable subset of Rn. Let subscript V be a Vitali class of closed sets for E. And we may select a finite or countable disjoint union Ui from subscript V such that either summation of the diameters of Ui's are infinite, or the measure of E difference union of Ui is 0. Basically, it says that if we have a Vitali class for E, if E is a measurable Hausdorff measurable subset of Rn, then we have a finite or countable union of disjoint sets such that E difference that set is almost 0. If the measure of E is finite, then we may also have this inequality, which you can see there's a relation with our second lemma, which we will use to prove the second part. All right, let's jump to the proof of the theorem. So first, let's fix rho. We may assume that all of the elements in our Vitali class has diameter smaller than the rho, because we're only interested in smaller sets. If we are looking at larger sets, the implication may be easier to prove or mathematical. So we may think without loss of generality, we're working with a specific rho small enough, and U's, we're looking at U's whose diameters are smaller than rho. So again, we choose Ui's inductively exactly in the same manner as our first lemma. First, we pick our first U1 to be any member of our Vitali class. And then we define the U1 to be the supremum of U's such that U's are in our Vitali class, but their intersection with our U1 is empty, just like our first lemma. So because we're constructing things very similarly, they are going to have very similar or identical properties. And we pick U2 such that U1 intersection U2 is empty, and U2 is also in our Vitali class. And the diameter of U2 is larger than U1. Again, we can do this because this supremum, we, without the soft generality, assume this supremum exists because they're all smaller than rho. So this supremum can be at most be rho. And the second supremum, again, can be at most be rho. and goes on. So suppose we have chosen for our first M elements in our subcollection. And let's say the M, the supremum, like this, at the mth step is 0. Then our claim is E is actually a subset of our union of UIs at this step. So first, let's prove our claim. Because if there exists such X that sits in E but not in our union, because our Vitali class is consisting of closed sets for each delta I, now we can pick deltas. We pick them to be 1 over 2i, anything goes to 0 as I goes to infinity. There exists U delta I in our Vitali class such that the diameter of U delta I is smaller than delta I, that it's non-zero, by the way, because it's in the Vitali class. But since the M is 0, this means, right, so here X is also in U delta I. So for each delta I, we have a U delta I that contains X, and its diameter is smaller than delta I. But since the M is 0, this means for any U that includes X, they have non-zero intersection with the union UI because of our construction, because this diameter is 0 for every U with such properties. So since diameter of U delta I is non-zero, its intersection must not be empty. So for each delta I, we can pick an xi in the intersection of U delta I and our union. It's possible because for each delta I, this intersection is non-zero, because diameter of U delta I is non-zero, but the supremum of U delta I, such that U delta I intersection the union, sorry, I messed things up a little bit for the audience. All right, so what we're saying is, since the M is 0, which is the supremum of U's such that U's are in the Vitali class, and U intersection the union UIs is empty. This is 0, which means for any U delta I, the intersection between U delta I and union of UJ's, like this, is non-empty. So we can pick an xi in each intersection for each delta I, for each I. But as i's go to infinity, delta i's go to 0. But each U delta I also contains X. So as delta I goes to 0, xi's go to X. But since these xi's are in the intersection, they're also in our union. But our union is closed. It's a finite union of closed sets, so it's a closed set. But it means if xi's converge to an X, which they do, then X must be in the union as well, because closed sets include all of the limit points. So X must be in our union. That is a contradiction, because we first assume that X is in E minus the union. So such an X does not exist. Namely, E is a subset of our union if our construction terminates at a finite state dm, of course. But then, if this happens, then we're done, because it automatically concludes our theorem, because E minus the union UI is just the empty set. So its Hausdorff measure is just 0. So let us assume that it does not terminate at a finite step, and it goes indefinitely. Now we're gonna use some of the properties we talked about in our first lemma. Since it doesn't terminate. Let's say the summation of its diameters is finite. If it's infinite, then we are again done, because that's also in the statement of our theorem. So let's assume otherwise. Then for each I, we can pick a ball with the center in UI, with a radius 3 times the diameter of UI. This way, we can see that UI sits in BIs. And here's our claim. We're going to prove this using the basic properties we derived in our first lemma about this construction. So if X is in here, then there exists a U not intersecting any U1 and UK, because we are stopping at a finite step. So there exists a U that doesn't intersect any of these. And X resides in U. Since UIs go to 0 because of this fact, again, the n-term test, diameter of U must be larger than 2 times diameter of UM for large enough M, because they go to 0. But by the construction of UI, like in the lemma, U must intersect some UI, where I is larger than K and smaller than M. And this, because of the construction. If you recall our first lemma, because of the construction, U would intersect every, BIs would intersect every B in our subscript B. But in our case, U would intersect UI for I here, because it does not intersect any of U1 UKs. And if M is too large, and if I is larger than M, we would have this inequality. But for some I between M and K, we would have this inequality because of the construction. But then because of the Euclidean geometry, U would sit in BI, because we have here, BI has the radius 3 UI, and U is diameter of U is more than equal to 2 times diameter of UI, which means UI is in BI, but U intersection UI is not empty. And again, like increasing the radius 5 times in our lemma, because we increased the radius 3 times of the diameter of UI, we have U sits inside BI. So a bow claim holds, because X is in a U and U sits in some BI, and that basically says our inclusion here. So let's return to our measures. Then the measure of E minus union of UI is smaller than this guy here. This is true because this is a larger set that contains this one, and we're taking a set subtraction. So measure of a larger set that contains this guy here would be larger naturally. But since because of this inclusion, this would be smaller than here, but the I's are balls, so their Hausdorff measure is like this. And since BIs have radius 3 times UIs, this numerical value is equal to this guy here. So since this is independent of K at this point, we can increase K arbitrarily. Then right-hand side would go to 0. It could be made smaller than any epsilon. So this gives us the measure of this guy is 0 for any delta. So this proves our first part. So we found UIs that are disjoint such that when we subtract the union of ui's from E, their measure is 0. Or the summation of the diameters of ui's is infinite. All right, this proves our first part. For the second part, it's going to be a bit more direct because we're just going to use our lemma and our first part in A. If E has finite measure, then we can write E like this. So we subtract union ui's, and then we just add the intersection of union ui's with E. So this is just a property of the measure, and if E has finite measure, this happens. So here, in order to apply our lemma, let rho be the chosen real number corresponding to epsilon and E given by our second lemma. So if this holds, then we're automatically done, because then, if you recall to our statement, then right side is infinite, so whatever left side is, which is finite, is immediately true. If though it is not infinite, then from the first part of our theorem, we know that this guy is 0. And here, this is smaller, strictly smaller than this, because of our second lemma. And again, first part. So if you recall our lemma, it says that for the rho that is chosen specifically for the epsilon and E, any rho Borel cover, for any rho Borel cover, we would have this, which is true because of our second lemma. All right, so this concludes our theorem. And as I said, this is a useful theorem because it can be difficult to work with difficult covers. But if we can extract a Vitali class from a cover, then we have very nice properties with measures. So it's a useful practical theorem for measure theory. All right, thank you for your attention. Bye.